at least I think of it as being due to Penrose, who sort of one-upped Einstein in terms of summation conventions. The Einstein summation convention, you get to drop the sigma sign, and the Penrose and tensor network world, you get to drop all of the indices. They just go. So I've drawn a tensor network. The one at the top is the network is here, and on the right is the interpretation of it, which I'm going to tell you once and for all, and then after that you're supposed to understand what these things mean. The idea is you put in tensors. Tensor is just a thing that responds to indices with a number, so Tij or Tijk, and this tensor network, this picture on the left is supposed to represent a tensor with 4 indices, 1, 2, 3, 4, and the idea is that the indices go on these strings, which I've drawn in blue, and I'm going to try to keep always drawing my strings in blue, and you sum over any indices on strings that are not connected to the boundary. So the boundary, this strings are fixed, IJKL, and the other ones you sum over. So here we have the explicit formula for this tensor network. It's the sum over A, B, C, D. There's an A there, a B there, a C there, and a D there. And then you take the product, you contract the tensor according to the usual idea. Right? So that's it. So now from now on, and down here, I have a tensor network where I've added one more convention, which is I don't put the tensors in anything, so I don't have to worry about their shape. I just have the strings crossing there, and then I put the name of the tensor in one of the many regions about that point. And this has the advantage of you may have been upset as I was saying this about the lack of starting point for these indices. Right, I said Tijk, but which one comes first? Well, I said this one comes first, but that was no good reason. But so the idea is I put the name of the tensor in the region right before, in clockwise direction, the first of the indices. So this is Tijkl, S, whatever it is, A, B, A, K, and so on. Okay, and of course that doesn't work for the outside index, so if I have to, and I don't think I ever will, I will indicate that by putting some kind of mark. That means this is the first one. Okay, everyone happy with that? That's tensor networks. Any questions? Right, so let's go on. Oh, dear. How this happened. Oh, I do know how this happened. I know how this happened. I copied a whole lot of files from one talk to another talk, and overcopied some of the files. So it might go ahead and machine. This is not at all the file that's supposed to be there. So the inner product, never mind, I can fix that very easily. The inner product between two tensors, you just take the tensors and you put, say, R there and R star there. And R star is just, you take the R tensor and then you read the indices backwards and you take the complex conjugate. And if you follow the conventions, this is nothing but sigma R I J K L R I J K L. This is the inner product. Of course, in general, you have an R in there. Yeah, this one. A lot of these tensor networks have interpretations to other things such as matrix multiplication and so on. Right, now moving on to quantum spin chains. What are they? A quantum spin chain is a linear arrangement of quantum things. You call them spins or qubits or q-trits or whatever, depending on where you come from. Each of which is called a spin, and the states of the spin, they are quantum spins, and they're given therefore by a finite dimensional Hilbert space H. Okay, so there's this little h, which is the spin state space for an individual spin in the chain. When you put things together in the quantum world, you take the tensor product, so that if you have a spin chain with capital N spins, then its Hilbert space will be given by the tensor product, the N spins. Now, the tensor product is just a tensor product. So in order to actually introduce the linear structure, and this is going to be an important theme, you have to do something that tells you which one is next to which one, what order they're in. And one of the things that accomplishes this is something like a nearest neighbor Hamiltonian. So this is a Hamiltonian, which is of course supposed to be a self-adjoint operator, and it consists of a sum of interactions between spins and their nearest neighbors, where little h is an element, is a linear, I've probably got it here. Little h is from h tensor h to h tensor h. This is a self-adjoint operator expressing the energy operator between two neighboring spins. And you just move it along the chain in a notation that I think is probably familiar to everyone. It's common to impose periodic boundary conditions, so the last spin is connected to the first, or maybe identified with the first, and the whole chain can then be thought of as sitting in an annulus. We may be a bit sloppy, I may be a bit sloppy about telling you when I'm applying periodic boundary conditions and when I'm not. So you're confused, just stop me when I ask. In terms, now, just to make sure we've got these tensor networks idea straight, the action of h on the vector psi is given by the following. So this is a tensor network picture of that Hamiltonian. Here's the vector psi. It's in this capital N-fold tensor space, so it has capital N blue strings. Here's the little Hamiltonian, which has two ins and two outs, and I've thrown in an I and I plus 1 here to say where it's inserted. So that's the diagrammatic notation for this local nearest neighbor Hamiltonian. Now, none of this talk would be real without, or would be somehow motivated, be anchored without some kind of discussion of a beautiful piece of mathematics and physics that was due to the St. Petersburg School back in the 1980s. So I just want to briefly run through that again, so that you know. If you've seen it before, then it will warm your heart to see it again. If you haven't seen it before, then you'll be learning something rather beautiful. So the idea is this: if T of lambda is an element of n of h, sorry, I got that wrong. H tensor h. H tensor h. That's a typo. It's a typo. The tensor h didn't come out. This should be n of h tensor h. It's one of these crossing things, like the Hamiltonian itself. Depending on a parameter which we call a spectral parameter, so that's important. I don't want anyone to be confused about that. Depending on the spectral parameter, then the corresponding transfer matrix, the transfer matrix comes from statistical mechanics, and I'm not going to go into the origin, is the following operator. So this is a tensor network picture of it, where I have simply suppressed T of lambda, and I've just written it as lambda. Seems like a good thing to do. So you notice this T of lambda is occurring in this position on all these places here. And maybe I've imposed periodic boundary conditions so that it wraps around. Okay, so this is a picture now. I hope we've seen enough tensor networks to know what this means. And that is the transfer matrix T of lambda. It's an operator on this big tensor space. It's an operator on this space here, this H. So it has that number of legs at the bottom going in, and this number of legs coming out. Of course, when you apply it, there's some implicit sum of all of these intermediate indices. Okay, now we're going to make the hypothesis that T of 0, we take T and that 0 is one of the values of the parameter, and that T of 0 is this particular tensor. So what is the meaning, how do we parse that? Well, the tensor indices have to be constant along the edges, along the strings. So this is a tensor network where if you have I here and J here, it's going to be 0 unless I happens to be equal to J. And similarly, if you have K here and L here, it's going to be 0 unless K is equal to L. And if they are equal, it's 1. This is a product of delta functions tensor. Okay, and we're going to suppose that t of 0 is equal to that. Then what happens? Then we do the, let's see, the product rule for differentiation. Does Newton have anything to do with that? It's Leibniz rule. Leibniz rule. Of course, Newton must have known about it, but probably people knew about it well before Newton anyway. So anyway, by the product rule for differentiation, and here it's important that this lambda guy actually does vary. Just one value of lambda is not enough. Then we can differentiate t at 0, like t prime at 0. And this, by the Leibniz rule, product rule for differentiation, this is the sum of I. You just evaluate it at 0 here, and at the ith and I plus 1 slots, you differentiate it. And if we call little h, we call it t prime of 0, then that goes in there. Okay, so this is looking awfully like a local Hamiltonian. It's the derivative of the transfer matrix at 0. Okay, but it's not quite, because these things are going to they're not lining up straight vertically. So we correct that by dividing by t of 0 inverse t prime of 0. And that, lo and behold, is a local Hamiltonian where the little h is t prime of 0. Okay. Differentiate this at 0, we get a local Hamiltonian from a transfer matrix. And in case I went too quickly, I'm being very gentle in the first 15 minutes or so of this talk, I'm going to actually do that thing. So here's at the top here, this t0 inverse, and at the bottom, there's the derivative. So you'll see that when you straighten out these lines, this picture becomes that picture. Remember that composition of operators is just stacking the tensors. There's the intermediate step. Right. Now, this is nice, but what does it buy us? Well, the matrices T of lambda are said to satisfy a Yang-Baxter equation if the following is true, and this is important. For each lambda and mu, there is a third sigma, value of the spectral parameter. So for every lambda and mu, there is a third, such that the following is true. So this is just tensor networks, one on the side, one on the left, one on the right. You'll notice that sigma you can think of this as sigma going from the top to the bottom and flipping around lambda and mu, effect of the spectral parameter. And then there is a very cute argument, which I'm not going to do. It's so well known. I mean, just I'm worried about time if I start getting into it. It takes about 3 minutes, but that's more than I have. But anyway, a cute argument, the Yang-Baxter equation, this little commutation relation between T, and so this is a cubic equation on the entries of this tensor T of lambda. It implies this amazing global commutation relation that T lambda T mu equals T mu T lambda. So these operators, transfer matrices, with different values of the spectral parameter, actually commute. And pictorially, oh, by the way, periodic boundary conditions are important here to make this argument work. But pictorially it looks like this. So here we have lambda, this is T lambda, this is T mu, this is T mu, this is T lambda. We'll go that way. Right, so but this has wonderful consequences. What this means is that T of lambda supplies, by algebra and calculus, okay, a large family of operators commuting with the Hamiltonian. Okay? And I'm not sure what I say it here, but you can also get more Hamiltonians. If you start differentiating twice, 3 times, and so on, you'll get Hamiltonians with longer range interactions than just nearest neighbor, but still local in some sense. And the fact that all the T lambdas commute, they therefore commute with all of these local Hamiltonians, so you get this wonderful big family local Hamiltonians and all these operators which commute with them, which are going to have common eigenvectors because of the commuting, and therefore eigenvalues that are the eigenvector will be independent of lambda. So the eigenvalue will be some function of lambda, and then the work really starts, I guess, in trying to figure out what these eigenvalues actually are. Okay. So that's the so-called quantum inverse scattering method due to, well, I guess the name Fadeev was often associated, but there's a whole group, Sklianin and others, in St. Petersburg, who put this all together and built on an analogy with Baxter's use of the Yang-Baxter equation in solving models. I could say a lot more, but once again, I want to get to the end of what I have to say. So I just want to point out at this point that this, everything that went into the arguments, right, I did all those arguments, and all I did was pictures. I did that calculation that the logarithmic derivative of the transfer matrix is a local Hamiltonian. It was entirely done by pictures. We just assumed that T of 0 is this picture, and then the manipulated pictures. So it's possible, therefore, to make sense of all these arguments without referring to specifically to tensor networks. The arguments will work for commuting transfer matrices. And so you can do this, and one such framework grew out of subfactors and is known as planar algebras. But you can do it in languages of tensor categories, provided you have enough structure to make sense of all the diagrams. But certainly, planar algebras are heaven for this kind of argument. You can even get somewhere on doing the next step in the program, this algebraic beta ansatz, to figure out what the eigenvectors and eigenvalues are in the planar algebras. So a lot of the equations I will solve in the rest of this talk are actually in this framework of planar algebras, whose greatly increased flexibility will have some advantages. So there's many more examples of planar algebras than just these tensor networks. So I'm going to take advantage of that to get at the simplest examples by using slightly more general pictorial formalism than the tensor networks. But if you don't want to learn about that, don't care. There's plenty in tensor networks. So just forget planar algebra, just think you're dealing with a tensor network if you want to. Now, I've come to a certain point in the talk, and I want to extract a lesson from what we've been saying so far, and then go on from there. And the lesson that I want to take, the message that I want to take from these ideas, is that the fundamental object here is the transfer matrix. Okay? It's the transfer matrix which has all of this wonderful data, and the individual local Hamiltonians are just sort of sitting there underneath it, but it is supplying all of this data. So what I'm going to want to look for in the rest of the talk is the appearance of transfer matrices. And now I assume that if you want Hamiltonians, you can get them, and so on and so forth. So any questions at this stage? Okay, good. Well, actually, it's probably not good. That means that either everyone has seen it all before or completely lost. So it's bad. So maybe I should wait for someone to ask a question. Then I'd be using up all my time. I'm stuck. All right, let's go on. One of our ambitions in what follows will be to construct transfer matrices with continuously varying spectral parameters, and this is very important. You have to, in order to do calculus, you need to be able to let the parameter vary. You know, these people who do knot theory and think they've done something when they've got a brain, well, you know, that just doesn't cut it at all. Compatible with certain scale invariance properties. And here's the big one. Since the Hamiltonian, we know that Hamiltonian is the infinitesimal generator of time translation, we have the mantra, the transfer matrix determines infinitesimal time translation. Okay, so keep that in mind. That's the message from all what we've done so far. The transfer matrix determines infinitesimal time translation. The Hamiltonian is the generator of one parameter subgroup, which is time translation in the quantum world. Right. Now, we changed topic a bit, and I want to look at scale invariant states. So, let me say the following construction was originally motivated by a quest, which has so far been unsuccessful, to construct conformal field theory directly from a subfactor. So this is sort of spin-off. This is going to be taking that work, seeing that it fails, but being seduced by some of the beautiful mathematical structures going on and going off in another direction, and hoping that that will have physical implications, which it may. It is here. It can also be thought of, if you don't want to have anything to do with subfactors, as a reversal of the idea of block spin renormalization, which goes back to Kadanoff and Wilson. So what we want to do in order to get conformal field theory from the subfactor, one wants to build up a Hilbert space associated with a circle by building it up from Hilbert spaces associated with finitely many points. You see, subfactors give you Hilbert spaces associated with finitely many points on a circle. And in conformal field theory, at least the chiral part of it, says you've got to have a Hilbert space associated to the circle. It was very tempting to try to take these finite dimensional Hilbert spaces for n points from a subfactor, let the points on the circle become dense, and hope that you get the Hilbert space of the conformal field theory in the limit. Well, as I said, that's a very tempting thing to do, and I've been trying to do it for quite a while now, and it hasn't worked. And I can prove that this approach, so anyway, to this end, we need a way, whatever you do, you need a way of increasing the size of a given finite set. So if we want to let these finite sets on the circle become more and more dense on the circle, you've got to have a way of taking n points and adding a point. Or so taking one of the points and doubling it, tripling it. That's the first thing we're going to be looking for. So what are we going to use to get that? Well, we're going to do this using a linear isometry, which is an endomorphism, here I've got it right, from H to H tends to H. So it's a bit less than Hamiltonian. It's endomorphism, it's a linear map from R, from H to H tends to H. And the idea is quite simple. If you take a spin in your chain and you want to double it, replace it by two spins, then you simply apply this endomorphism, because in the right spot. It goes from H to H tends to H. Okay, so the adjoint of R would be the operator in block spin renormalization. Right? That would be the operator that says, oh, whoops, this is bad. This was another result of copying these files. Remove that blue line in the middle. That's not there. Okay, R is something that goes from H to H tends to H, and R star is supposed to be the identity. So once again, that line, let me just put my hand over it. Well, it still comes out of my hand, I can't do it, sorry. But that line is not there. It's just in your mind that it's there. Okay, this is the condition R star is equal to the identity. So that's the key isometry condition expressed in tensor networks of the unit of R. But you see, once you have that, once you have such an R, you can go ahead and embed, so this is now the idea becomes important. Equipped with this R, we may now construct an increasing family of Hilbert spaces, Hn of dimension, the dimension of the original H to the power of 2 to the n, by embedding that 2 to the nth tensor power and the 2 to the n plus 1th tensor power by the following tensor network. And here it is. We have a psi as a vector with 2 to the n legs, and to each of those legs we apply R, and we get out a tensor with, in this case, 8. We've doubled the number of legs. So we've gone from one tensor power to the next tensor power. Okay? So, whatever we've done, we have achieved part of our ambition. We have defined, by taking the inductive limit, obviously, we've defined a way of getting a Hilbert space associated with infinitely many points on the circle. And so now, if we choose a vector omega in H, little h that we started with, it defines a vector omega in each tensor to these tensor things via the above embedding. We'll call it the vacuum vector. So let's have a picture of it. I thought we had a picture of it. Well, hopefully a picture of the vacuum will come up soon. The Hilbert space defined as the direct limit of the above increasing sequence of Hilbert spaces will be called the semicontinuous limit of the quantum spin chain. So this name came out in discussions with Tobias Osborne and Wilfred Vidal. who are people who are working in the game, the opposite game, the block spin game. So it's called semi-continuous, and obviously where that came from, we were trying to get a continuous limit, but all we got was this limit with, infinitely many vector-dense set of points, and we were unable to bridge the gap between that and the continuum. So now I'm going to try and do some propaganda here. So this, you can believe it, I've been saying these words for a couple of years now, and every time I say them I get slightly more convinced that there's actually something to it. But so here's the idea. If you had a quantum spin chain, a macroscopic quantum spin chain, then about how many spins would it have in it? About 10 to the 8, 10 to the 9. Not 10 to the 23, right? 10 to the 23 is, that's three-dimensional thing. It's the cube root of that. So you've got 10 to the 8 spins in a thing about this long. Well, you can't see them individually, but you just sort of get your glasses out, a couple of pairs of glasses, and you start to see graininess. So my question is, I ask you, what is a better model for that? Is it something where you have like lots and lots of spins, an infinite family of spins on the diagonals, or the continuum? Okay. If you're doing conformal field theory, it would be the continuum. If you're going this way, that I'm proposing, this totally heretical way that I'm proposing today, then you would say, the continuum is not the right model, this is the right model. Okay. So as I said, I'm trying to be provocative in propaganda in this business. By the way, if you do this and you want to construct subfactors, piece of cake. You get your subfactors in all their glory, but not in the continuum. Okay, so here's this picture of the vacuum, which is important to have in your mind. So here's our vacuum vector in the very lowest of these Hilbert spaces, which is just this H. And then once we put two legs above it, we've got H in the next one, and so on. So each time we double it, we got H, and it's the same vector, right? Because we're identifying them according to this identification. So this is a picture of omega in the whatever it is level of this inductive limit, and H, omega in the limit is to be thought of as this sort of going on infinitely often, and the vectors in this inductive limit are supposed to be thought of as finite-ish perturbations of the vacuum. The vacuum is very important. And from now on, you see we have all these R's. Well, we're going to fix an R, and we're going to suppress R. So so this picture would be replaced by a picture without the R's, and they're just implicitly there. There'll be a trivalent vertex, and it's supposed to have an R on it. So, and now here's the bad thing. At this stage, the semi-continuous limit and the vacuum vector have nothing to do with the placement of the points on the line, right? This is just some graph, and I could go back to this omega, and I could grab hold of this whole branch of the tree, and I could just sort of shake it like that, and let it all spin around and so on, and it's still the same tensor product. Okay, so the order of these points on the line has not been addressed. Okay, and that's ultimately why this doesn't work as a continuum limit procedure. But so people in the block spin renormalization, they got there before me, of course, with this tree. They encountered the same difficulty. And Evenbley and Vidal invented the so-called MIRA, which is the multi-scale entanglement renormalization ansatz. They have some wonderful names, which introduces unitary disentanglers to tie up the branches of the tree. I was just in Savannah not so long ago, and so it reminds me of all that moss on those beautiful parks, the trees in the park. So here's a picture of the somewhat schematic picture of the disentangler, right? You have all of these branches of the trees, and they, instead of being independent, they get connected by all this moss. So the moss in this picture is the disentanglers of Guiffre and Vidal. And if you want an actual picture of what the mirror looks like as a tensor network, then just Google it, you get squares. Okay, now, so Vidal et al. Obtained good numerical in agreement with CFT. They can, remember, their philosophy is the opposite. They have some Hamiltonian or something like that, and they're trying to get its behavior by blocking the spins together. And so the calculations come down to some finite calculation at the bottom. And they can look for endpoint functions and critical exponents, and they get very good numerical agreement with CFT. They get the freedom to put disentanglers in R matrices, and if they optimize according to some strategy, they get critical exponents correct to several decimal places, and so therefore I guess one has to believe them. Unfortunately, that would be great, and maybe that's where we should go in looking for this continuum limit for a subfactor, but the trouble is all of this stuff is numerical, and at the end of the day we will end up with a theorem about subfactors. So it would be sort of just as difficult as going some of the other ways that have been proposed. I don't see any advantages at this stage. Of course, if there's a breakthrough in mirror technology, we should be aware of that and jump on it. All right, but now here's the important remark. As soon as we are thinking about how motions on the line, for instance rotations, act on the picture, then we are actually dealing with states of a quantum spin chain where the spins are next to each other. So if we think of taking all of these spins and just rotating them, moving them along by one, then as soon as we talk about moving along by one, those strings are on a line. They're not just dangling on these leaves, on the branches that go off to infinity. So we are in fact doing physics here, provided we talk about motions. And I've been trying to sell the Thompson group as a replacement for the diffeomorphism group of motions in this picture. But today, all I'm going to look at is the rotations, which are in the Thompson group, of course. But I'm just going to, that's all I'm going to consider. So anyway, end of the day, we have these states in this vector space, this semi-continuous limit, and we want to investigate them, see what physical properties and mathematical properties they may have. Are these states relevant for physics? Okay, I'm trying to sell you with these states that are in this, this spin doubling inductive limit Hilbert space. Well, they certainly exhibit scale invariance, right? They were constructed by this scale invariant process. So, according to the yoga of criticality phase transition, which the physicists have been hammering us with for donkey's years, since the 50s, that scale invariance and so on is supposed to happen at a phase transition. So we might look for these kinds of states cropping up near a phase transition. But Araki showed that in one dimension, you don't get any phase transitions as a result of temperature change. There's no critical temperatures. But there are these things called quantum phase transitions, and they happen at absolute zero temperature.
I'm sorry, I didn't get how you get the states. You said now we have some states.
The states are just vectors in this semi-continuous limit.
Whatever vector it is.
For instance, the vacuum. The vacuum is a nice state.
Okay. I mean, that is somehow scale invariant, but if you just take something, I don't see...
It's scale invariant. Keep going with the question.
So, I mean, the vacuum vector is a nice one, but so that's the state you're looking at, or any
Well, it's any of these ones that sort of eventually start looking like repeated.
Oh, okay.
So you could say this is an inductive limit. Just look at stop at any point in the inductive limit, and the vector in that one is scale invariant.
Okay, thank you.
Okay. So one might look for these. So here's my question. This mathematics, these parameters that are going to come out of the scale invariant vectors. If this theory is to be any good at all, one place to look for seeing those parameters would be to look at systems at a quantum phase transition, which means absolute zero, which is of course impossible. But you're supposed to. The idea is that you're supposed to see this quantum phase transition as the temperature gets towards absolute zero. See what it looks like. So, one could even think of proposing experiments to physicists as a result of the calculations that we're going to do, to see if these states are actually sitting there in these systems near the quantum phase transition. Also, if the detailed spin manipulation required by quantum computers is achieved, the gates available should be enough to put a system in such a state. So what I'm saying here is one of these scale invariant states is not likely to occur just in the course of nature with if you just let a spin chain evolve at some ordinary temperature, you're not going to see any of these funny guys. But if the quantum computer people say, well, we can construct these gates which allow us to form very, very specific states of a quantum spin chain. Well, if they can do that, then they can surely, to goodness, make these states as well, and maybe investigate them. Okay, this R, of course, would just be a kind of gate. Then that we call the gate. Right, so now I want to get down to it. Do some mathematics after all this seminar and propaganda. I want to do some calculations, and I'm going to focus on the following calculation. I'm going to take the rotation by 1 over 2 to the n. Okay? So 1 over 2 to the n simply means we take this lattice with 1 over 2 to the n, and it's periodic, so we just move along by one single unit, one tiny little bit of unit. And then we're going to try to figure out what happens as n tends to infinity. Okay, the reason why we focused in on this is obvious. If we were trying to produce a continuum theory, then this rotation as n tends to infinity should be tending to the identity. It's supposed to be smooth. So let's see what happens in this picture. This is the number I want to get. And I've told you all that with the tensor networks, I've told you everything we need to get this. And I want to do this calculation in gory detail because I've sort of, I've sold the farm on it. This is the thing that has convinced me that something really neat is going on. So I'll try to convince you that it's a good calculation and do it so that you actually understand what's going on. Do it very slowly. So suppose that psi and eta are actually in this approximate Hilbert space. So they're nice scale invariant states. The following, so I'm going to give you a picture for the rotation of 1 over 2 to the k plus n plus 1. Well, the 1's there to be correct, because I stole this from a paper I actually wrote. Normally in a talk I wouldn't be so fussy. So it's 1 over 2 to the k plus n plus 1, where we illustrate here for k equals 1, so it'll be in the Hilbert space tensor to the 2h. So we're going to look for a vector with how many legs? 2 legs. And then n equals 3. So, yeah, so the point is this, that, right, if we take a vector in one of these 2 to the k dimensional Hilbert spaces, whatever it is, n to the 2 to the k, we want to rotate it by something much, much larger than the number of legs it has. How do we do that? Well, we embed it up until it has enough legs, and then we rotate. Okay, so this is the picture. Okay, so I want you all to, come back from whatever you're looking at the internet and look at this picture. Okay? This is the picture for that inner product. Remember I said inner products, you just join them up over there. So I've done that. At the bottom here is the vector psi, okay, which I've embedded in a sufficiently high Hilbert space in order to be able to perform this rotation. And at the top is eta, which I've also embedded in a high enough one, and I've done the rotation. So these legs here, instead of matching up, and then if they matched up they would cancel by unitarity, they've gone along one. Okay, whoops. And I've put in these dotted blue circles the part that I want to focus on. You'll notice that what's in the dotted blue circles is the same everywhere. And it's really the same because I used Xfig copy and paste to actually make them the same. So, not only do they look the same, they are the same. Right, so now I'm going to blow up and blow up one of those little blue regions and see what's inside it. There it is. I've done a little bit of isotopy to it, but that's what it is. If you want to go back, you've got good eyes, and you'll see all I've done is I've taken what's in that one of those little blue regions and I've made it so the line connecting one blue region to the next blue region has gone from being at an angle to being horizontal. And this is what it looks like. Like this. So if I call this thing X, what's inside the picture, that's a tensor network or an element of the planar algebra, then this is the picture for that inner product. So that tensor network is a number. There's no boundary things. Everything is contracted. So that's a number, and that is that inner product. Okay. So what do we recognize? Our friend that I spent so long hammering at you, the transfer matrix. There it is, right in the middle, smack in the middle. X, 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 X with the horizontal things and the vertical things. So we recognize the transfer matrix T2 to the n plus k of X. So thus we can say that the transfer matrix determines the infinitesimal space translation. Remember that mantra? Transfer matrix determines infinitesimal time translation. So we've got, here we've got, if we happen to be in this one dimension where time is equal to space, and we've got the same thing. But it's determined that in the topsy-turvy, according to Wikipedia, is not spelt with this E, by the way. It's another misprint. It's just topsy-turvy. So we're in if time happens to be equal to space, we have recovered our previous mantra that the one dimension, the infinitesimal generator of time translation is determined by the transfer matrix, but it's all screwed up. It's not quite the derivative, it's this limiting procedure. Right, so now the great thing, of course, is not to stop there. We can actually go ahead and take that transfer matrix and in this picture and apply, notice that it consists of all of these little blocks put together with X in the middle. Think of this as a renormalization procedure, which has put together two of these X's and has come out with another X, and observe that after one round of renormalization, this inner product that we were after is this picture here. Okay, where Y, remember what Y was? Y is this. So if I call this Y, and I'll put Y in all of these things, and all of a sudden there's a whole lot less. We're actually on one scale coarser, and then you just keep on going. Okay, continuing in this way, we see that this inner product is equal to the transfer matrix, where you've got rid of all of these ones that you want. You just keep on going until there's none of these doublings, all of the R's are gone, and you get psi transfer matrix eta at the appropriately renormalized value of X. So we start with X, which is this little picture of the X was this. That was X. And then we hit it successively with this tensor network, and when we've got rid of all of them, we're calculating exactly our inner product. It's this operator, this transfer matrix, which is in between psi and eta. So to get the limit, which is what we're interested in, right? To get the limit, we just let n tends to infinity. So we iterate this renormalization transformation and see what happens to it. And that will give us the infinitesimal behavior of the rotation. Okay. So as I said, this is the procedure I like so much. I'm betting the rest of my career on it, probably. In order to proceed further, we need to do a specific model. Okay, we could say, well, we've got this renormalization transformation. We iterated. What happens? What happens? Well,
one question about the formula.
Sorry?
The psi and eta in the formula, they have to somehow, when you let n.
So they're just fixed. They're just sitting there throughout the calculation.
Formally, don't you have to kind of map them up using the R a couple of times?
Well, we did that to start with, right? So let's go back through it again, just in words. We had psi and eta, and in order to see what the rotation did, we had to map them up with some R's. And do this tiny little rotation. But then, what we observed was that we got in the middle of the transfer matrix, and we could just get rid of it by applying this renormalization. And so all you get is psi, transfer matrix, and eta. But the value of the transfer matrix, the lambda we're putting in, is the result of iterating n times this renormalization transformation. So you notice it's the difference between this figure, this was after one round of renormalization, and this figure. You notice those x's are a bit smaller than the y's. Okay? Because they're smaller on a coarser scale. You just keep on going, right? And now apply this renormalization again. So this bunch here, it's the same transformation applied to y, and then that's gone. And then there's only one thing of ours left, and we do it again, and that's gone. And at the end of the day, we end up with simply the inner product of the renormalized n times x, the transfer matrix of that between psi and eta. So in order to figure out our limit, we just have to understand what this renormalization transformation is. Well, that's going to depend on the model. What the model is and what you choose for R. So let's go ahead and now get a specific model. Right, now one of the troubles in the game is that in general you're going to have at least a one parameter family and maybe a three parameter family of choices of R. So, but we could do ourselves a big favor if we could find a place where there was only one choice of R. And we could just look at that one. And there is such a place. And if there's some planar algebras, and if you're not happy with planar algebras and you want to stick with tensor networks, then that's fine. Choose dimension of H equals 3 and simply suppose all the tensors are fixed by the action of SO3. And it's a fact that we all know from representation theory that if you take the three-dimensional representation of SO3, tensor it 3 times, then there's a unique SO3 invariant vector. That's the R. That's the R. And it's unique up to a irrelevant phase. Okay. Planar algebras will give you a whole lot more. In fact, if you think of it, it's really just, in this case, just quantum groups. You can do SO3Q. In this case, R is rotationally invariant, so we never even have to worry about where we're putting it in. Just use a trivalent vertex. And for this, you can see a very interesting paper by Morrison, Peters, and Snyder on categories generated by a trivalent vertex. And so we're now going to begin by calculating the renormalization transformation explicitly. Okay, so remember, what was the renormalization transformation? It was a transformation, let's go back to it, oops. There it was. It goes from the space with 4 legs to back to the space with 4 legs. In this category we're talking about, that space is 3-dimensional. So we want to calculate this transformation of a 3-dimensional vector space. And we need a basis of that vector space. And here's the basis. One of them is our friend, which is called X, and the other two I think we've seen also. They're tensors with 4 legs or elements of the corresponding planar algebra or tensor category or whatever you want to call it. So an arbitrary element that we're going to apply the renormalization transformation to is a vector of the form P times this one plus Q times that one plus R times that one. And Morrison, Peterson, Snyder, and lots of other people, this is, baby Kuperberg, would tell us the relations that we can use to do all the calculations. And here they are. If you cap off a trivalent vertex, you get 0. There's this IH relation between the trivalent vertex itself and, of course, unitarity, which is this guy here. Okay? And, if you're in this game, if you're doing TQFT or anything, tensor networks, then you'll probably smell that there's enough to, if you want to do any calculation, all you have to use is these relations. So here it is. So we just go ahead and calculate, and this is R in this basis. So we start with an element PQR, then when we renormalize it, according to this, it's a quadratic, homogeneous, 3 homogeneous quadratic polynomials. This one is the coefficient of X, this is the coefficient of this element, and that's the coefficient of that element. Okay, D, what's D? D is the quantum dimension. Note that D is the quantum dimension, which will be 4 cos squared pi over n minus 1. For n equals 6, 7, and 8, things go wrong for smaller heads. And D equals 3 is the case of the SO3 invariant tensors. Anyway, you've got these 3 quadratic homogeneous polynomials, and I would argue that this is a canonical dynamical system. We're not looking at this dynamical system because we want to see some kind of Julia set or Mandelbrot set or something. We're looking at it because it arose as the only thing, R was the only tensor possible in this SO3 invariant world. So this is, these functions, whatever they are, this is obviously, you could improve on them, but they're canonical.
So what was A?
A.
Parameter, R of A. Is that D?
R of A, oh sorry, yeah, so this is a cutting and pasting problem. A is this guy here. A is P plus Q plus R. I've been calling it X, I think, before. But in my haste to prepare these transparencies, I did some cutting and pasting from my paper, which is not yet existent, at least to anyone but me. We see that this rotation is determined by iterating, the lesson of it all is we simply iterate the above dynamical system quadratic dynamical system and see what happens. And that will give us the infinitesimal rotation. Okay, so let's see what happens. Some calculations show that there's two rather special behaviors. The first is if d equals 2, so that corresponds to way back in the prehistory of this category, the index 3 subfactor. D ends up being 2 for that one's the first one, which you can do stuff. And what happens is r to the n of x is this guy, specifically. What happens is the renormalization simply flips it between it and its adjoint. And its adjoint is obviously the one with that and that, the one that would be for the other rotation. That's it, it keeps on going like that. So you can evaluate this limit simply by taking that picture that you get right at the bottom and just putting this particular x, this one in, and then that's the answer. Some non-zero, typically, well, in general, be non-zero answer. Okay, but that's very atypical behavior. It turns out that in all of the cases that I have been able to get my hands on, the limit of this thing is actually 0. It's actually 0, and it's 0 quite quickly. It goes to 0 as 2 to the 2 to the n, right? 2 to the minus 2 to the n. It's rather rapidly going to 0. I have been unable to determine exactly how fast it is. I know it's order of 2 to the minus 2 to the n, but then there's a factor in front of that, and the best estimate I could get was n to the 14 over 15. So, but maybe some polynomial. I'm not very good at that, and it turns out that the dynamical systems people aren't very good at it either. Surprised me. In any case, we see that this rotation tends to 0 as n tends to infinity, which is exactly, this is the no-go thing. Oh, sorry, that paper is published. I'm stealing all these formulas from this no-go paper, which is on the article. So it tends to 0, but it's supposed to be tending to just the inner product of sine eta if we're getting smooth. So it smooths out. All right. So it's hard to know what to make of these results, and as I said, physically one might try to look and see if this is actually happening at a quantum phase transition. I'm not enough of a physicist to know how to test for this correlation between the spin state and its shift by 1. But you could think of it as being some kind of exponential spatial white noise, because it just says that if you shift it 1, it's totally uncorrelated. Okay? Or in a more positive vein, you could say, well, this is also some kind of exponential resonance. Unless the two things line up exactly, they will be independent. So there's the cup half full, cup half empty things. In either case, even if you have to give up and say it's white noise, it's very structured white noise, because you can take this inner product and then normalize by the rate at which it's tending to 0 to get a quadratic form in the sense of Barry Simon as a function of psi and n. So I said that I didn't know how fast it tends to 0, so that's a problem, but we can take advantage of the vacuum and renormalize simply by how fast the vacuum goes to 0. So we define these quadratic forms here on the fine dimensional things. So this is the ratio of this by this. This is a bilinear function, or sesquilinear or something. And the theorem is that there are two quadratic forms on HR, Q plus or minus, such that, I was actually cheating here a little bit, such that the limit of this quadratic form here is actually Q plus and the other one is Q minus. So from the point of view that we're adopting, these should be called the topsy-turvy momenta, because they are the topsy-turvy generators of renormalizing. H you get by rescaling, you take the derivative. So here we're sort of taking this topsy-turvy derivative, we're getting two operators, so they should be...
But they do not converge to the same thing. I mean, they're different.
They are different, yeah. Actually, you'll see I've got a bit more coming up. They're obviously, to get them, you're going to apply this renormalization transformation. They're obtained, so here it is, by examining R on projective space, where it becomes a pair of rational functions of two real variables. Right, so we had everything was homogeneous, so it's really something happening on two-dimensional projective real space. The two quadratic forms correspond to an attractive orbit of period 2 under the renormalization thing. Okay, so now I'm running out of time. So so I'm now going to give you a picture of this projective two-dimensional space and some idea of the relevant points and how the transformation acts on it. So here it is. I'll put q equal 1, so I'll set something to infinity there. And here's the projective space, and there's lots of other stuff, but it's out there. Here's the pair that these things are tending to. This is the two quadratic form things here. This is the attracting cycle. And here is x. Actually, x is at infinity, so we have to, in order to get it on this picture, we have to hit it with one arm. So here's x. This line is sent to infinity. And this is a repelling fixed point with complex eigenvalues. So things are going to loop around it as they go away from it. Points will generally tend under iteration of r squared, to either q plus or q minus. So this is what happens. If we start with r plus, this is the phenomenon. This is going to start converging to this cycle, so we'll start going around there. And scale invariant fractal behavior can be observed. So it's a rational function. So we would expect Julia sets and so on, but you've got to make sure, right? This is something that's not anyone. I'm not allowed to. I was told what these parameters have to be by upstairs. So I actually figured out this is the plane or region of the plane, the sensitive region of the plane, divided up into red goes to one point and blue goes to the other for the square of that transformation. The transformation is going like that, so its square will be tending to either one or the other. And this is just one picture, this is one scale, but I assure you, if I change scale on that, at least 10 orders of magnitude I've done it, and you get the same looking picture, just maybe rotated around a bit. So there is some fractal things there, and that's some kind of...
So you have little choice in the vacuum vector, right? Does it
Yeah, everything. Vacuum vector in this case is no choice at all either, because we've put ourselves in this planar algebra, and it's just the relevant space is one-dimensional. If you like, tensor networks, there's only one invariant vector by SO3 and C squared tensor, C cubed tensor, C cubed. So it's clear the calculations we have done. So the quadratic form by t of lambda will tend to t of mu as a fixed point. Right. Oh, sorry, I went very quick. I'm going to take another few minutes, Di. No. I said I am. We got to 30 out of 34. We're doing it. So this raises the question of whether there is a scale invariant transfer matrix defined on the semi-continuous limit with continuously varying spectral parameters. So we go right back to the beginning. We had this transfer matrix. It was no good to just have one value of lambda. We want to get a continuous value. Now, if we want to construct a scale invariant transfer matrix, it seems like a good idea in light of what's going on, we want to make sure that it exists. So here's the idea. It is clear from the calculations we have done that the quadratic form t of lambda, if we define t of lambda now for any of the value of lambda on the n-fold, 2 to the n-fold tensor power, will extend to a t of mu, provided this back iterate provides a renormalization transformation sends lambda, mu to lambda. That's just another statement of the calculation we did. But what this means is that if we want to take a t lambda, we could define it here, if we want to extend it on the bigger and bigger Hilbert spaces, we have to back iterate the transformation. So this is another big deal in dynamical systems. These concepts that Julia said, Vanderbilt said, and so on, are not at all irrelevant. They are sort of brought naturally to us by trying to construct this transfer matrix. In this particular case, there is no guarantee that a given point in R2 is the image of R. We're not on the usual complex dynamics, which is on one-dimensional complex projective space. Things are surjective because of solving polynomial equations in complexes. We have to check that we can back iterate as much as we like. And what happens is we can. If we choose this point, so this is on the cycle, so this is one of its preimages, but it has another preimage because it's quadratic transformation. That one is up there somewhere, and that is a choice of sign when we solve the equation. We stick with that sign, and this guy will keep iterating and back iterating, so we'll go very rapidly to this repelling fixed point and spin around it because it's got complex eigenvalues. Okay, so the corollary is that in the neighborhood of this region, we can define a scale invariant transfer matrix in the sense of quadratic forms with a continuously varying parameter. Right, so now I'd just like to finish with a bit of candy. We're in this real predictive space, and things are not. Everyone knows, right? The dynamical people, the thing that they study to absolute depth and beyond is rational functions of a complex variable defined on one-dimensional projective complex space. We weren't in that beautiful realm, but we can get there simply by doing a slight change on the setup. In fact, there are scale invariant models which we end up with rational functions on CP1 on the nose. And in fact, they arise in a physically natural way. Remember that when we did this chain, we said that we'll take a spin and we'll blow it up to 2 spins. You might say, well, what about that spin? We might want to have it there, still there in the new chain. And if you do that, the very simplest examples you get this procedure for doubling your spins. This one just goes, once it's there, it stays, and it's only the new ones that double. Okay? And if you do that, then you can use, instead of having to go with this fancy SO3, you can use ordinary Temporally-Lieb, which in spin things is SU2 invariant tensors, and choose R to be any element with 4 legs satisfying R star equals 1. So we've lost a nice feature that was a unique R, and it's come to have 4 legs. But if you do that, the relevant transformation is a quadratic transformation from a 2-dimensional space to itself, and it's a, it's a polynomial. It's a rational function of complex variables. And here it is. If I choose the Temporally-Lieb parameter to be 2 cosine pi over 8, which gets you into the good stuff, then this is actually what it looks like. This is a rational function that you're supposed to iterate to get all this transfer matrices. And I managed to persuade mathematics to give me a picture of this Julius here. So there we go. That's the thing that you'd be back iterating along that set in order to construct your transfer matrix, scale invariant transfer matrix in this case. So I'm going to stop there because I've already had the time. Thanks.
Are there any more questions or comments?
Yeah.
Did you construct the Hamiltonian with these?
Yeah, that's why I cheated and I said what we're really after is a transfer matrix. So if you try to construct the Hamiltonian matrix, you really get into trouble. And the trouble goes back to this fact that these branches originally were flopping in the breeze. They didn't have the moss, the savanna moss. The physical consequence of that fact that you're on the tree is that the relevant distance between this spin and this spin on the line is the tree distance. It's not the physical distance. And points that are very far apart here are actually quite close on the tree. So when you start to do a Hamiltonian, you can get them, but they're rather non-local beasts. Now, the quantum computer people say, hey, so what? But I would rather like to see local things. So I'm betting my money on the transfer matrix as being the fundamental thing.
You said you get a T of lambda at the end, but somehow I haven't seen where the lambda came in. So what was lambda? So how did you get the parameter between it?
So, right. So, I was going very quickly there. I start with, I want to define a scale invariant transfer matrix. Okay, so I simply take a value of this lambda, and I decide that I'm going to take that T of lambda on a certain level, the Hilbert space. So I go up in I think here's how scale of Hilbert space is going up. I decide I'm going to start here, and I use T of lambda for this particular value of lambda. You choose it, I don't care, any value. Then I want to extend that to the next level, okay? And I said somewhere in there, I said that's possible if we take T of mu up here, where the renormalization transformation sends mu to lambda. That's where you get into the back iteration. So in order to construct this thing on the whole limit space, you've got to be able to back iterate indefinitely. And in that case, the SO3 case, that's absolutely not true. A lot of the points, if you start back iterating, it's not surjective. The transformation is not surjective, so you get stuck. But for that particular, those ones I showed in that picture, you can back iterate all the way to infinity and you tend to this repelling fixed point, which you could send to infinity if you wanted to. Yeah.
Can you comment maybe a bit more on this mirror thing?
Oh yeah, sure.
How does it work? And
All right, I'll tell you about the mirror. So I just sort of ran out of time, otherwise I would have had a nice slide to do this. So I just drew a picture of what they do. They have all kinds of versions of this, just like I have all kinds of versions of what's going on with the tree. But, so these guys were drawing these pictures, the same pictures as me, all along, but they were thinking the opposite direction, right? They were thinking renormalization, block spin. I was thinking of creative spin. So the mirror goes like this. We start with the tree. Let's go down a couple of generations. So this is your tree structure. There's no moss. So the moss we're going to take a 4 box, represented as something like that, and we're simply going to put it in here. Periodic boundary condition will take care of this, but then we've got, since we put it in there, we've got to also put it in here, at all levels, at all scales. Okay, so these things are called disentanglers, and they screw up the tree structure. So all of a sudden, this nice correlation that you get between this one and this one by going along the tree has been destroyed because you can't get from there to there without going past one of these disentanglers. And the 2-word summary of what they've done is that if they fiddle with this guy and optimize according to the things coming out of the various renormalization ideas, the DMRG and so on, then they start with some Hamiltonian, and they use this data actually comes from the Hamiltonian they're trying to work with. Then they claim that they get, well, I'm sure they're right, they get critical exponents to very high accuracy. The nice thing about it, the relation to what I was talking about was, if you have the mirror upside down here, and you just put it like that, then all of these things will cancel and you get 1. By construction is a unitary, so if you put that with its star at the bottom, that would go away. Okay. You can't do that rotation calculation that I did because unfortunately it doesn't work quite so nicely. But what you can do is if you take a local observable, so suppose you have an observable like that, so that's observing one spin, and then you look at its expectation value, then look what happens. All that happens is little things here, right, and all the rest of the network actually cancels. And it turns out that this doesn't propagate very far as you change scales, and you only get up to a few sites apart, blocks. And you keep doing that, and you get just a finite little thing at the end you have to compute as the limit, as n tends to infinity. So that's how they get their endpoint functions.
But the computation you did with like a 1-shift rotation.
That doesn't work, no. No, that's something that seems to require the tree. Which is not unnatural, right? Because if it worked, then you wouldn't have a continuum limit. And they're saying that they really do get conformal field theory from these mirrors. So it's just even bleed and bleed down.
Okay, so I think we'll have a coffee break now and then start again at 22. So.